Welcome everyone to today's webinar. This is Piotr speaking. Today we are just starting a new series of meetings aimed at showing you the practical applications of our software. As you probably noticed, the session subtitle is with expert. This means that meetings will be led mainly by our NFX customers, our clients. However, for those of you who are not yet NFX user, we are also open for you. So if you have some interesting project that you are working on and you would like to share with us and everybody, we are also open to support you, and from the next time we can grant you special Midas NFX license, and then we can collaborate together. There is with us Mr. Panson Poon, who is our guest speaker and who will lead the main part of the session. He will talk about experimental model and finite element analysis, modal correlation, and tuning of the model. And as the example, we will use car wind deflector part. Before we start to talk about resonance, let's look on the presented clip. The video shows the structure response to the given frequency drive. As you can see, under the influence of a single frequency force, each of the rows reacts to different frequency value. The real vibrations are loads which are combination of excitations of different frequency values. And those components which are close to resonate frequencies can lead to disaster. So resonance, as we can see, is the reason, is the cause or at least a contributing factor to many of the vibration and noise related problems can occur in structures, prototypes and other machinery. To prevent such scenario, the prototype or structure must be checked for resonance response. So we can do this on experimental and numerical way. In Midas NFX, resonance can be studied via following types of analysis. I'm talking about eigenvalue and frequency response. So eigenvalue is the basic one which allows to grasp resonant behavior. A modal analysis, which is exactly the same, determines the vibration characteristics like natural frequencies and mode shapes of the structure or a machine component. It can also serve as the starting point for more detailed and complex analysis types like transient or spectrum analysis. Correlation between numerical and experimental analysis can be done via modal assurance criterion. So this option is available inside the eigenvalue settings inside NFX. MAC, which is abbreviation from modal assurance criterion, is a statistical indicator similar to coherence function from the statistics, which can be very powerful when it's used correctly, but also can be very misleading when used incorrectly. So the MAC, as I said, is often to use pair mode shapes derived from analytical models with those obtained experimentally. MAC value can change from 0 to 1, and 1 signifies perfectly correlated mode, but generally it's accepted that the value of greater than 0.9 is considered as a good correlation, and everything which is less than 0.05 is uncorrelated. So during this session we will see how this feature can be used in practice. Now let me introduce our today's guest. So Mr. Panson Poon is a senior engineer with PhD degree, specialized in noise acoustic vibration analysis. He served as an engineer and R&D manager in various US-based and startup companies. Recently, he has been involved in many loudspeaker and high-end audio projects. His company is widely recognized in Hong Kong, and they are focused on electronic and consumer goods market. Once again, welcome, and please proceed with your interesting topic.
Thank you, Piero, for introducing me and the company. Hello audience, once again my name is Panson Poon. Today I would like to talk about my recent study of a car door wind deflector. A deflector is a common aftermarket accessory for private cars to avoid rain and debris getting into cabin when you need to open the windows slightly for fresh air. You may notice higher wind noise after the deflectors are installed. The deflectors change the aerodynamic of your car and create air turbulence along themselves. Vibration of the deflector would also generate secondary audio noise. To investigate vibration-induced noise, it is necessary to know the natural frequencies of the deflector, which frequencies fall within human sensitive hearing band. In addition, knowing the mode shapes of the deflector provides useful information for optimizing the structure. For instance, we may add a rib here or there to strengthen the deflector to move a resonance to different frequency or minimize its vibration level. We could also change the mounting points to tweak the mode shape to move the resonance spots far away from your ear, closer to the window, so that you can hear lower noise. Midas NFX is used to perform numerical modal analysis. In the study, the deflector model is built directly in NFX using its preprocessing tools. A physical deflector is underwent experimental modal analysis. Measured data are used to correlate and validate FEA model. Before we dig into the wind deflector case study, let me give you some warm-up information. Here is a stainless steel ruler. The ruler's one end is clamped by a heavy wires. The other end is free to vibrate. This is a fixed free beam or so-called cantilever. This simple structure is represented by 1D bar element in Midas NFX. A 1D line with 7 nodes is drawn. Visualization of the bar elements is shown in the right bottom graph. 4 nodes are companion of the 4 highlight points in the graph of the actual beam. First 3 bending modes obtained numerically are shown in the three graphs. Twisting and literal modes are not considered in this simple warm-up example. Notice there is a node at half length of the beam for the third bending mode. This is also one of the measurement locations of the beam. That is point number 1 here. The experimental modal analysis is carried out as follows. An impact hammer strikes a point near the fixed end. A force sensor is embedded in the hammer head for measuring input excitation load. This excitation location is fixed through the experiment. Displacement laser sensor measures 4 highlight locations. This is so-called roving sensor method. For each strike, we record time history of input excitation and displacement waveform. Collect data are preprocessed to obtain frequency domain frequency response function. The FRFs are then processed by curve fitting algorithm to predict natural frequencies and damping ratios. Mode shapes are derived from the data as well. In this simple example, we only measure 4 locations. As pointed out just now, a node of the third bending mode is one of the measurement locations. We will observe very low displacement at this location for third bending. If we want to obtain good quality measurements, spatial sampling density needs to be increased. For instance, we should also measure points along this section and more points everywhere. In general, we should try to avoid measuring a node of interest modes or resonance. For instance, this point, we should try to avoid it if the third bending mode is of interest. Now we have two sets of data. One is obtained by Midas NFX. The other is from the experiment. We can compare them in different ways. Numerical comparison in this table shows natural frequencies obtained by NFX and the test. Good agreement is seen. This is indeed expected for this simple structure. Let's see the animation of measured mode shapes. This one is for the first bending mode only, the second bending mode only, the third bending mode only. Since one of the measurement location is at a node of this mode, and we have just 4 points measured, one may think along this section the bin is stationary. This is obviously a wrong conclusion due to insufficient spatial sampling. The right bottom graph shows combined vibration. Different mode shapes obtained numerically and experimentally, we can perform correlation among them. This is the Modal assurance criterion, MAC, represented by a matrix. In general, we have main diagonal of values close to or equal 1. Theoretically, other values are 0. Non-zero values of them could be due to measurement noise or insufficient response points measured. The MAC matrix visualized as a 3D bar chart is illustrated here. Now, we are ready to take the main course. Typical wind deflectors are given in these slides. The one used in the study is this one. The deflector model was created directly in Midas NFX using its CAD drawing tools. Lines were used to sketch the outlook of the deflector. Trim was used a couple times to remove unwanted section of crossed lines. Translate was used to move several lines in the Z direction. The outcome was a 3D graph, 3D geometry made by lines. Once we have all the lines drawn, we generate faces for closed edges as illustrated in the video. Different lines are in different colors, as we can see here. From the Make Face tool, we select edges that form a closed region. Sometimes we may not select all the right lines for the side face. In this example, in this case, we need to select again. And sometimes we need to zoom in to see whether we have all the lines select. Now we have everything select correctly and a face has been made. In this illustration, we have all the other faces create and the complete geometry of faces is seen. The deflector is mainly made by ABS plastic. Along its upper edge, there is an adhesive foam tape for bonding to car door. We can use shell or plate elements to model the main body of the deflector. This minimizes memory consumption and computational load. Well, this simple deflector structure would indeed not create problem for modern computer if 3D solid elements are used for the whole structure. On the other hand, the foam adhesive should use solid element given its geometry, where the ratio of thickness to width is not suitable for using shell elements. In this structure, there is a contact between the upper edge of the ABS body and one side of the foam tape. This is modeled by a weld contact because of the strong bonding strength of the 3M tape. In this case, the ABS body is the master of the contact. The complete CAD model with mesh is shown in this slide. The model will be analyzed without constraints to grip rigid body modes. The mesh model is used for modal analysis in NFX. One of the missions of modal analysis is to locate an optimum location to mount the accelerometer for use in experimental modal analysis. First four bending modes are presented in this slide. Another four bending mode shapes are shown in this slide. From these mode shapes, we can avoid mounting the sensor near or on nodal lines as illustrated in the warm-up example. The lower right corner, seems to be a good choice for mounting the sensor. In experimental modal analysis, the accelerometer is fixed at the location which is highlighted by the red dot, and this is suggested based on the modal analysis done in NFX. In contrast, impact hammer strikes multiple locations of the body. This is namely roving hammer method. The test setup can be seen in this graph. The structure was suspended by rubber bands to mimic free boundary condition. Test equipment mainly consists of a lightweight accelerometer, impact hammer with hard tip, and flexible hardware-software data acquisition system. The accelerometer mass is only 0.5 gram, which eliminates mass loading effect. The hammer tip is made of steel. Once we have all the hardware or hammer connect, we make couple strikes on the body to test whether we have the system running properly or not. The input spectrum, the input force spectrum shown in the top graph here, is a flat spectrum up to about 300 Hz. This is a typical spectrum for good impact, which is equivalent to a single unidirectional pulse. In some strikes, multiple hitting occur. In that case, comb filtering effect would be seen in the force spectrum. You will not see a flat region here, but comb filtering light spectrum up and down all over the measured bandwidth. The bottom graph is the response spectrum. Resonant peaks are seen clearly. The deflector under test was suspended by rubber bands. When we view the test object as a lumped element, the rubber bands and its form a spring mass damper system. Very low frequency resonance will be observed. We need to discuss them since they are associated with the rigid body motion. Here is the video clip of the motion. As you can see, the whole deflector moves up and down altogether. There are 79 locations for the hammer making strikes. Each location needs 5 good hits. Sometimes multiple hitting occurs. Therefore, we need more than 5 strikes. As you can imagine, this is a time-consuming process. The acquisition system exports measured data in CSV file format. All the CSV files are preprocessed in MATLAB. In the processing software, we form 2 matrices. One is input matrix, and the other is the response matrix. This graph shows 5 input pulses, 1, 2, 3, 4, 5, and the corresponding response waveform. The 2 matrices are processed to obtain frequency response function matrix. The frequency response function is the ratio between response, acceleration in this case, to input force. Given 79 measurement locations, there are 79 FRF. These graphs show all the FRF overlaying together. The highlight line is the average of them. We can see these 79 frequency response functions have resonance at some common frequencies. We pass the frequency response function matrix to curve fitting algorithm to predict natural frequencies and damping ratios. The algorithm starts from first order up to the order set by the user to locate the frequencies of any possible resonance. This is a stability diagram of such search for a band from 10 to 200 Hz. Maximum order was set to 15. For the first single order trial, the algorithm could only find the frequency and damping for the peak near 50 Hz. This is interesting to see that 3 peaks in the upper band are not recognized by the fitting algorithm. To solve the problem, we can resort to more powerful algorithms or each time fitting a narrower band. This is another example of the stability diagram. This time, the FRF frequency response function of the points along the red line are considered. 4 peaks are identified for their frequencies and damping ratios. A crosser mesh of the FEA model is prepared in Midas NFX for making comparison with measured data. Animation of the measured data is being played here. The red line represents the vibration along the upper edge of the deflector. In this area, the ABS material is thicker than the other area of the deflector. This is why you can see the red curve vibration level is larger than the blue lines because the area along the red line has thinner material. In the future, we would like to investigate the structure of the deflector when it is bound to a hard surface. It is similar when the deflector is in use. Also, we would like to compare numerical time domain response analysis in Midas NFX to measured time domain data. Midas NFX has been used extensively in many projects I handled. For example, it is used to study nonlinear behavior of rubber surround, the suspension of loudspeakers drivers. I also use it to predict unknown elastic modulus of material. It is also used to investigate vibration characteristics of loudspeaker enclosures. And recently, I use it to compare with experimental modal analysis data. The software helped me in a software project at critical stage to understand the speaker mechanical limit. The driver is being used in smart speaker. From the beginning, the software is recognized as a complete full-feature FEA code, including pre-processing, linear, nonlinear, static, dynamic analysis, and it is with an affordable price tag.
Thank you, Mr. Panson, for this interesting content. Now there is a Q&A time. Your questions can be stated via chat section. We are waiting both with Mr. Panson to answer them.